When an object moves in a straight line under constant acceleration, its motion appears mathematically perfect to the observer. We describe that motion using a standard one-dimensional kinematic relation, v squared minus u squared equals 2as. Here, u and v are the initial and final speeds. The letter a represents the constant acceleration, and s stands for the total distance traversed. But this equation only describes the geometry of the movement. How do we actually relate these speeds and distances to the physical energy required to create them? The equation has a strict limitation. It contains no information about the object's mass or the force pushing it. It strictly tracks the path, ignoring the physical effort. To calculate energy, we need to inject the rules of dynamics, the specific study of how forces and masses interact, directly into this purely kinematic framework. We will start with a mathematical translation. We multiply the entire kinematic equation by a new factor, half the object's mass. By distributing m/2 across every term, we alter the structure of the relation. Look specifically at the right side of the equal sign. We have isolated the object's mass times its acceleration, or ma. This specific pairing allows us to invoke Newton's second law. Newton's second law states that the net force applied to an object equals its mass multiplied by its acceleration. Because force equals mass times acceleration, we replace the ma with a capital F. The right side is now simply force multiplied by distance. That single substitution directly bridges the gap. We have converted an abstract description of speed and distance into a concrete measure of force applied over a displacement. In physics, this product of force and distance is called work. It represents the actual physical effort exerted on the object. Real objects rarely travel in perfectly straight one-dimensional lines. Their movements and the forces pushing them happen in three-dimensional space. A force might push at an angle, while the object displaces in an entirely different direction. We need a way to measure exactly how much of that force contributes to the movement. To do this, we use the scalar product. The scalar product, or dot product, is a mathematical operation that multiplies two vectors to yield a single number, calculating the specific component of one vector vecting along the direction of the other. Applying this to our expanded derivation, the terms become vector dot products. The equation updates to incorporate the specific directions of the velocities, the force, and the displacement. The left side of this equation represents a change in state. The term 1/2 mv squared is kinetic energy, the energy an object possesses due to its motion. We denote this total change as delta K. The right side, the dot product of force and displacement, is our precise definition of work, denoted by a capital W. This leaves us with a highly efficient relation. Final kinetic energy minus initial kinetic energy equals the work done. Specifically, this equation refers to the work done by the net force, meaning the combined total of every single push and pull acting on the particle. We have successfully translated Newton's second law. Instead of analyzing acceleration at a specific instantaneous microsecond, we can now analyze the total shift in an object's energy between 2 points in time. This theorem offers a severe mathematical shortcut compared to traditional force and acceleration analysis. To calculate motion using only force equals mass times acceleration, you need continuous data. You have to know the exact magnitude and direction of the force at every moment. The work-energy theorem relies on a state change concept. It strictly requires the initial energy state and the final energy state. Whatever happens in the middle, the specific path the object traces or how the forces fluctuate, does not change the final energy calculation. This bypasses missing variables. If a force constantly changes magnitude or direction, tracking its moment-to-moment acceleration is difficult, but tracking its overall work is simple. The theorem becomes a primary tool for solving complex mechanical systems, where the continuous internal data is either unavailable or too chaotic to measure. Let's test this theorem on a system with highly variable forces, like a single raindrop falling through the atmosphere. Consider a drop with a mass of exactly 1.00 gram. It falls from a height of 1.00 kilometer and hits the ground at an impact speed of 50.0 meters per second. During its descent, the drop is subjected to two opposing forces. Gravity pulls downward with a constant force, while the air pushes upward with a varying resistive drag. This split shows the forces at play. A bar chart tracks the work done by gravity, resulting in exactly 10 joules of energy input. Now look at the final kinetic energy. The impact speed reveals the drop only kept 1.25 joules. Gravity supplied 10 joules, but the drop only kept 1.25. That leaves 8.75 joules completely missing from the drop's final state of motion. The math has to balance. If gravity performed 10 units of work, the work energy theorem states that the remaining energy must be accounted for by the other forces in the system. We can pinpoint the exact effect of the air resistance by setting the total change in kinetic energy equal to the work of gravity plus the work of the resistive force. We isolate the unknown variable. The resistive force equals 1.25 joules of kinetic energy minus 10.0 joules of gravitational work, resolving to negative 8.75 joules. This negative sign proves air resistance performed negative work, continuously sapping the drop's kinetic energy. We quantified this exact energy loss without ever knowing the aerodynamic drag profile of the raindrop. The air resistance varied wildly depending on the drop's speed and shape at any given second. But by measuring the simple state change from the cloud to the ground, we captured the total effect of that invisible, fluctuating force. Constant forces are easy to calculate with standard equations, but the work-energy theorem thrives in messy, real-world conditions where variables change unpredictably. All that missing energy doesn't just disappear into nowhere. Instead, it physically manifests as heat and drastic structural deformation upon impact with the ground. The work-energy theorem serves as the physicist's master ledger. It guarantees that every joule of physical effort, whether constant or chaotic, is rigorously accounted for in the final calculation.